Hey guys, okay, we are starting some harder material. This is going to be definitely the hardest material of the class because this is something that you guys probably don't know very much about. So we're going to jump right in talking about the winds. So the way that we're going to start here, and I'm going to go ahead and share the screen. I'm going to go to our wind systems. This is one of the modules in the Comet, or the METED, sorry, the METED stuff. And we're only going to do the first couple of them, but I definitely want you to join me on this. So open this up. And then over here, it's printable lesson, which is what we want to do. And it just talks a little bit about the wind. So the very first thing is, what is wind? Okay, wind is the horizontal movement of air. Now, I shouldn't have to say to write down everything. As I kind of looked over the beginning parts of your lecture notes, I think you need to be a little bit more careful and add a little bit more than you have been, just to make sure that you're doing it well. So what is wind? And highlight this and say wind is the horizontal motion of air. Now we use terms of advection, if you recall, to talk about the transfer of energy by the motion of the air. So when wind is blowing horizontally, if the air that is over there is warmer than it is over here, then you're going to be bringing warm air advection, or warm air is going to be coming into this location. The same is true with cold air advection. So we want to make sure that you understand what wind actually is. It's the horizontal motion of air. Now, sometimes we do talk about up and down motions, and that would be convective motions. And we don't usually talk about vertical wind, even though that is technically correct. I'm going to worry about the horizontal motion. Now, over here it says, wind is the horizontal motion of air relative to the Earth's surface. This movement of air results from small and large scale temperature differences, as well as from the Earth's rotation. So we're going to be talking about that and what that is. And that's really the next 3 lectures are going to be getting into understanding how the atmosphere works, how it moves. Now, the thing here, wind is defined as the direction from which the wind is blowing. Okay, so if the wind is from the south, it's going to be a south wind. So it says north wind refers to which of the following? A wind blowing not to the north, but from the north. Okay, and then if it's from the west, then we're talking about westerly. Okay, so whenever you see the suffix ly, lee, that means it's blowing from the west. A westerly wind is from the west. If I had a word, W-A-R-D at the end, it would be westward. We're moving like toward some direction. But we're going to talk about winds from where they come, and they're blowing from the west is a westerly wind. Now we can look at a whole bunch of stuff that shows you how the air moves. And instead of showing you this, I can certainly do something a little bit different. I can show you a satellite picture that we have from our website. And if I do something kind of cool like this and let it loop, right, it gives you an idea of how the air is moving. This is a satellite picture of water vapor imagery. And you get the idea that there's this flow from the southwest over across the mountains, and maybe over us it's out of the northwest. And then there's a circulation here. So you can kind of see how the air is moving by looking at cloud parts and how that all is going to play itself out. But that's how we're dealing with winds. Okay. Now there's lots of scales of motion. So remember, the largest scale is planetary, and then we got synoptic, and then we have mesoscale. So lots of things to deal with in terms of the wind. And we're going to need to know the difference between the scales of motion for winds because they're affected by different forces. Now, if you go over here, it says, because of the Earth's curvature, the tropics receive more heat than the poles. That's because the Earth is a sphere. We've talked about this. And then there needs to be a flow to do that, to move that excess heat, warm air, to areas where it's cold and vice versa. Now, we did look at this before when we had the trade winds, if you remember the northeast trade winds, or the prevailing westerlies. But over here, we've got circulations in the atmosphere. And over here, this is kind of important. We have air rising at the equator, and it sinks around 30 degrees of latitude. Now, keep in mind that when air is rising, we know that's low pressure. When air is sinking, that's high pressure. Well, what gives us fair weather? High pressure does. So around 30 degrees latitude, that's going to be where all your major deserts of the world are. Air is sinking and it doesn't rain that often. So the Sahara Desert, the Middle East, the Gobi Desert, our desert southwest and into Old Mexico. In the southern hemisphere, the Great Sandy Desert of Australia, and there's the Kalahari Desert in southern Africa as opposed to the Sahara in northern Africa. Those are all around 30 degrees latitude where the air generally sinks. Now, do you remember the word for sinking air? It's called subsidence. So make sure you kind of re-emphasize some of these words so that you know them. Now, air rises at the equator, and there's a lot of water vapor at the equator. That's the tropics, the major oceans, and warm water. So you get a lot of thunderstorms in that region. And you could actually get that up north too, and then the poles. Notice the air sinking at the north and the south pole. Believe it or not, the poles are considered deserts. They're cold deserts, but they're deserts nonetheless. They don't get very much rain at all. Now, over here, we need to know, why do the winds? What's the direct forcing of the winds? Air moves because of this force called the pressure gradient force. The pressure gradient, if you recall, is a change in pressure over a distance from here to there, okay? And that's what you need to know about a pressure gradient. So here's the thing. Air wants to travel from high to low pressure. That's always the way that it's going to be. Now here they talk a little bit about these lines like a mountain ridge, and this might be confusing. I'm not a big fan of this. So what I'm going to do is I'm going to go over here to something maybe like this. This seems to be a good, simple diagram. So we're going to kind of take a look at this, and I'm going to use my pen here to show you what I mean. Now, this is an isobar, okay? So these are all isobars, and I'm going to look at this here, and where I've got my pen is 1,000 millibars. This line here is 1,000 millibars of pressure. And what that means is every place on that line is the same pressure. Now imagine that you're walking on it, and I want to make sure that you understand that way is north, okay? So this is a map view. We're looking straight down at the earth. We see an area of low pressure, similar to what we're seeing in this picture down here, when we've got the area of low pressure, okay? Now, if this isobar represents 1,000 pressure, any place inside of that isobar is going to be lower than 1,000 millibars of pressure. And any place outside of it is greater than 1,000 millibars of pressure. So I'm at this line, and it's 1,000 millibars of pressure. If I go to here, what does the pressure do? It drops. So notice we said air wants to travel from higher to lower pressure. Since the low pressure is in the middle, air is trying to come in. So that blue arrow is the pressure gradient force. It's saying the air wants to go toward the center. Now, do you remember we talked about mass continuity? The fact that when air converges, it's going to want to rise. Well, do you agree that all those arrows are pointing toward the center? They are converging toward the center of that circle. And therefore, the air is going to go up. That's what mass continuity says. Now, up here, it's got to diverge. Right now, we're focused on the air's converging and rising. So since the air always wants to go to low pressure, then we can always imagine that the air at all these points are all trying to come in toward the center. So the very first rule of all of our motion is air wants to travel from high to low pressure. And just so you know, from a visual standpoint, that's always going to be perpendicular to the isobars. Okay? Now imagine that I were to draw this. I'm just going to draw it over here, and I'm going to say, oh, look, I've got two isobars. Now remember, this is a top-down view. If we look at a different view, I'll show you what we have to do for that. This is a top-down view. So to the north, the north is this way, right? So we're going to go north, and I'm going to, type in north. I think I'm going to type in north, and I'm going to put a little arrow here saying that way is, oh, that's a big arrow. Let's not do that one. Let's make it quite a bit smaller. Let's undo it, and we'll just say that way is north, okay? So I'm at a point here, and I'm going to put a little dot here. Okay, I'm there. I don't know what letter that is. Let's just call it letter A, okay? So just so you have a reference. Now, what is the pressure of this isobar? The pressure, let's say, is 1,000 millibars. You remember millibar was the unit of pressure? So let's just say it's 1,000 millibars there. Over here, it's 1,004 millibars. So do you agree that the pressure is going to be greater to the south and lesser to the north? So if I said in blue, draw an arrow that represents the pressure gradient force, you would say the pressure gradient force points from south to north, and that is going to be from the south. So at letter A, what would the direction of the winds be if the pressure gradient force were the only thing acting on the air? And the answer would be southerly. It's a southerly wind. The winds are from the south. They are blowing from the higher pressure, which is south, to the lower pressure, which is to the north. Okay? That's assuming that there's no other force acting on it. This is just the start, so let's keep that in mind, okay? So I'm going to undo this. I'm going to erase this. I would say that you should draw this in your own notes, or you can clip it. By the way, if you use Shift, Windows key, if you've got a Windows computer, Shift, Windows, S, that will allow you to snip, and then you can put that in the paint and use that, insert that into your diagrams. I really want to see you do this well, okay? So this is a good thing, okay? So I'm going to erase this. You can always stop it and go grab it again. I'm going to look at something here, and I'm saying, all right, what if I put an area of high pressure here? So I'm going to put a big H for high pressure. And in this area of high pressure, I've got some isobars that go around it. That's too big of an isobar. Too fat. There we go. There's an H. And then over here's another circle around it. Okay, something like this. So what I'm going to say is, very much like these isobars, this one's going to be higher. So I'm going to go 1,004 millibars. And this one here is 1,000, oops, not 2,000, 1,008 millibars. Okay? So do you agree that the pressure inside here is more than 1,008? Now, it couldn't be more than 1,012, because then I'd see another isobar. But do you agree if I asked you on a test, which I will, what's the pressure in the middle? You'd say, well, it's more than 1,008, less than 1,012. So if I said draw in an arrow that represents the pressure gradient force, do you understand it's going from high pressure, which is inside now, to the outside, which is lower pressure? So the pressure gradient force at all these points is going to be like this. Do you agree that all these arrows are diverging? And Mass continuity says if they're diverging, then the air will have to sink and fill its place, subsidence, and that's what mass continuity says. So that's why high pressures are nice weather, low pressures are bad weather. The air is converging in low and rising, and air is sinking in high and spreading out, diverging. Review. If air is rising, what's the first thing that happens to it? You should be saying this in your mind. First thing is the pressure decreases as you go up. The box expands, and that air cools at the dry adiabatic lapse rate. Okay, so what's happening in an area of high pressure? Well, the air is sinking. So the first thing that happens to it is the air is moving down toward higher pressure downward. It's going to be compressed, and that's going to warm the air by 10 degrees Celsius per kilometer. That's the dry adiabatic lapse rate. Okay, so we're all good with that. I think I'm happy with the way that came out. So I'm going to go back to our wind systems worksheet. And now I'm going to look at something and I go, this thing called the Coriolis force. So right over here, that's what you got to know, the Coriolis force. So what do you need to write down about it? First thing, the Coriolis force is an imaginary force. It's not really there. It just looks like it is. As a result, that force is said to be apparent. So I'm going to write this in here for you. That's an apparent force. And what that word apparent means, it means it appears like it's real, but it's not really there. So on the Earth, we're spinning. If you've ever been in the English rotor, you know, one of the things where the floor drops out as you spin around, it feels like you're being stuck to the side. There's no force doing that. It just appears as though there are. So Coriolis force is very much that way too. But what that does is it causes anything that moves to turn to the right in the northern hemisphere. Okay? Anything that moves to turn to the right in the northern hemisphere. So I'm going to go back over here and I'm going to go back to this little idea. So bear with me as I redraw this. And I said this was 1,000 millibars. And this is 1,004 millibars. Now I said, well, which way does the air want to go? See, and I think I told you the air doesn't always travel from high to low pressure. I said the air always wants to travel from high to low pressure. So the air is trying to go this way. That's what it wants to do. That's the pressure gradient force. So to keep that in mind, I'm going to go pressure gradient force, PGF. Okay, I think, does that make sense? Air wants to go this way. But this time, as the air starts to move this way, and I'm going to use a different color, the air wants to go this way, but instead it gets turned to the right. As it ends up, it's not going to go toward low pressure. It's going to turn to the right, and so that is how the wind goes. Because the Coriolis force is going to be acting opposite. Oops, arrow. It's going to be acting opposite the pressure gradient force. So I'm going to type in this, and I'm going to say CF, which is the Coriolis force. Okay? So what we have here is two forces that are acting on the air. The first one is the pressure gradient force. The second one is the Coriolis force, which makes things want to turn to the right. It's not forever turning to the right, but for what you're going to learn, it's going to turn to the right of the pressure gradient force. So in this case, we have a couple of things now. So I'm going to write this down here for you. Because of the Coriolis force affecting the winds, the air will now travel parallel to the isobars. Oops, make sure I spell parallel with an extra E there. Parallel to the isobars. Okay? Low pressure is to, I'm going to go past here, the left of the wind, and the Coriolis force is to what? The right of the wind. So here, which way are the winds blowing? Winds are blowing that way. That's north. You better know your directions. I'm just telling you now. This is north. This is south. I hope you know your directions. What would this be? I don't know how to put this on here. This is west, and then this is what? East. So the winds are blowing from the west in this diagram. The pressure gradient force points to the north. Winds are from the west. Coriolis force points to the south. Okay? There is a balance between the PGF and the Coriolis force, which we call geostrophic. Oops, let's try to spell that correctly. Okay, there's a balance between the pressure gradient force and the Coriolis force, which we call geostrophic. It is a balance between the pressure gradient force and the Coriolis force. So what am I going to ask you? I'm going to say, what is the geostrophic wind? And the answer is the geostrophic wind is a balance between the pressure gradient force and the Coriolis force. What does that mean? It means the winds are going to travel parallel to the isobars. And the last thing you need to know about that is it follows the Buys-Ballot law. Okay, so what I want you to do is Google, what is the Buys-Ballot law? And you should see it's with the wind at your back, low pressures to your left in the northern hemisphere. And that's what I've said over on this page. So super important that you get that. Okay, so let's keep moving on for a second. I'm just going to hide the ink and move a little bit further. Now, in here, there's stuff about the jet stream, which I've asked you to do some of these things on the worksheet, so I'm going to let you do the worksheet on your own. Here's an upper level stuff, and this is going to be confusing because it's different than what's going on at the surface. But I'm going to skip that for now and go to this. I've got low pressure and high pressure. Now, what does that mean? The blue arrows here are going outward from the pressure gradient. That's the pressure gradient force, pointing outward from the high, like we've done. In the low, it's toward the center. But the air is going to start moving in different directions. This is a little bit confusing because it's not going parallel to the solid black lines, which are the isobars. And we're going to deal with that in a little bit here, okay? So this goes on to the right-hand rule and all this other stuff that we've talked about before. Okay, so that's something to get in here. But I want to go back to some information right here, okay? So I'm going to bring this back out, but this time I'm going to go to a whiteboard, okay? And I can erase some things, like I can erase that. And I want to write a couple things down. The Coriolis is only important, means, what does that mean? It plays a role in large scale flow. Okay? And what I mean by that is large scale flow is considered global or synoptic. The Coriolis force is not important in small scale winds. And what is small scale? That's mesoscale. That's what I want you to know by this. Now this is going to be tough, which is why you're taking good notes on this. The Coriolis force is important when I've got large scale winds. It is not important in small scale winds. In other words, over here, if this is mesoscale diagram, the Coriolis force is not there. What's the only force that acts on the wind? The answer is the pressure gradient force. So which way does the air travel? From high to low pressure. But if it's large scale, the Coriolis force matters. it turns the winds to the right, and therefore the air now travels parallel to the isobars. So I'm going to say something that you need to stop and write down, because this is the conclusion of what you need to understand. Air wants to travel from high to low pressure. And on the mesoscale, it does. But on larger scale flow, like global and synoptic, when the Coriolis force is important, the air travels parallel to the isobars, and it follows the Buys-Ballot law. That Coriolis force is balancing the pressure gradient force, and that's known as geostrophic. So that's the summary of what we've just mentioned. So I'm going to give you a little exercise here. All right, let's see how smart y'all are. I'm going to draw isobars like this. And I'm going to label the isobars. That's 1,000. That's 996. And I'm going to go to this point here, which is point A. Okay? And so the first thing I'm going to do is I'm going to say, whoops, I want my pen. I just want a dot. I don't want a line. I'm just going to say, all right, there's point A. First thing that you should do is in blue, and I want you to try to do this before I show it to you, draw the direction of the pressure gradient force. Okay, in blue, what would the pressure gradient force be? Okay, so you do that, stop the thing and draw it in. And then I'm going to show you what the answer is. That is the answer. Okay, 1,000 to 996. It's going from higher pressure, which is to the northwest, to the southeast. Now, if this diagram were mesoscale, do you understand there's no Coriolis force? It's not important. As a result, the air will be from the northwest. Air wants to travel from high to low pressure. That's the pressure gradient force in blue. On the small scale, there is no other force, so the air does travel from high to low pressure, which would be the same direction as the blue arrow, which makes the wind northwest. So I'm going to give you a test. I'm going to give you points on a map and say, what direction are the winds at this point? Really, what's the first question you need to know? You need to say, well, what size scale is it? So on the mesoscale, what would the directions be at letter A? And you'd go northwest. That's the answer. But what if this were global or synoptic scale? Well, then the next thing you would have to draw in is that there's a Coriolis force acting opposite. And it follows the Buys-Ballot law, with the wind at your back, low pressures to your left. So if this is synoptic scale, what direction are the winds? And the answer would be northeast. Northeast winds. Now, guys, listen. If you don't understand, if you didn't get northeast as a wind, if you didn't answer that, you need to go back and figure this out little by little. This is the hard stuff. And I'm guaranteeing you, I see classes do poorly on this because they don't really think through it enough to get it. You have a question, you have a problem with it, come talk to me. Okay? Let's do one more just for the heck of it, okay? But you know, this time I'm going to do a little bit different. Okay, so first of all, let me get rid of a couple things. I don't need that. Let's go here. What if this is what the isobar did? This time, they're curved. They're not straight. So what that means, first thing is you need to know what are the pressures. So I'm going to do this one as 1,000 millibars. And I'm going to say this one is 1,004 millibars. Okay. And I'm going to go to letter A, and I'm going to go to letter B, and I'm going to go to letter C at this point, okay? And I'm going to say, what direction are the winds at letters A, B, and C? Assume this is mesoscale. So you need to stop, figure out the answers. You tell me what they are. I'll give you a hint. First thing you should do is draw the pressure gradient force from high to low pressure. So stop, you do that, figure this out. Okay, I'm drinking some coffee. And now I will show you the answers because this is a virtual environment. I don't get to see how you do. It's going to be perpendicular isobars. There you go. And if this is mesoscale, how would the winds blow? The answer is in the direction of the pressure gradient force. So at letter A, on a mesoscale event, the winds are southwest. At letter B, they're southerly winds. At letter C, they're from the southeast. But what if this is large scale and we have the Coriolis force? Well, the first thing you draw is the opposite direction force. So the red is the Coriolis force. And then the black arrow says the winds are going to be with low pressure to your left, which is up here. The winds are going to be that way. Remember, they want to go this way, but they get turned to the right. The Coriolis force. Notice here too, folks, just keep this in mind, that your Coriolis force, oops, I don't want that. I can't try that way. The Coriolis force is always perpendicular. There's a little sign for perpendicular to the left of the wind, or to the right of the wind, sorry, to the right of the wind. So over here, the pressure gradient force is blue, the Coriolis force is red. Air wants to go this way, but it gets turned to the right. It wants to go this way, but it gets turned to the right. And right now, what we're saying is that at point A, the winds are northwest. At point B, they're westerly. At point C, they are southwesterly. And that's the answers to that question. But I want you to see something here. This is the cool part. And we're going to refresh this a little bit later. I'm going to draw a pen. If I follow the air traveling this way, do you see that in this feature, the air is turning? You see that it's curving. Which way is it curving? It's curving this way, which is counterclockwise, which is cyclonic. Okay, do you agree the air is curving cyclonic? Which means that this is an area of low pressure. And what I'm saying is that this is where I get my areas of low pressure. This is a cyclone. And that's what's going on, is the air's curving around that cyclonically. Now, super important, when the air curves cyclonically, we call that a trough. When it curves anticyclonically, we call that an opposite of a trough, which is called a ridge. Do you agree that troughs and ridges are part of something that is a wave? So in the atmosphere, we have waves, like waves in the jet stream. And we've got troughs and we've got ridges within that jet stream. The trough is when the air curves cyclonically, and the ridge is when it curves anticyclonically or clockwise. That's how we're defining this. So I'm going to trick you on the next lecture, but not with this one. You need to know those facts. Now, do you understand that there's a lot of information on these pages? Your job is to go and clean it up and write it neatly. And if you need to Google stuff and bring in images, do that, because that's what studying is about. Then you're going to know your notes, and then when I give you tests, you're going to be, I know how to do this. Don't rely that you're going to be able to use the notes and get answers on the test. You are making notes so that you are working hard to study the notes, making them good, and then you have something to access, but you've got to learn the material first. Okay, so I'm going to go here with this, and I'm going to skip ahead over here to where it says the next section. As I said, there's two areas. Now, local winds. Local is small scale, so those are typically mesoscale. So they're talking about a little bit of stuff. This is really important that you know this. I think this is on the worksheet. Most of the time during the day, air is going up a mountain or up slope, or if you're in a valley, it's going to go up the valley. What do you think happens at night? The opposite, down slope, down valley. Super important that you know that. So diurnal, 24-hour cycle, air goes up the mountain. At night, cold air comes down the mountain, down the valley. Watch the videos. And then they're going to talk about something here where it says aspects. Aspect is the slope of the mountain. Which way does it face? So imagine that I've got a mountain right here in front of you. This mountain is facing to the south. That side is facing to the north. Well, it's facing to where the sun is, so it's going to get warmest and coldest. It's going to be big variations in temperature, and that's going to result in faster winds. The north side doesn't. So something that you kind of want to follow through here. So they kind of go through this. I'm giving you some questions to go with this. Make sure you look through the questions, go through the videos. Don't skip over this. Try your very best. I'm not going to worry about giving you this now. Now, this land breeze and sea breeze, this is super important. Okay, we're going to see something here. I said draw a sea breeze, and I'm going to ask you this on a test. So what I need you to do is this. I'm going to go here, and I'm going to erase everything. And I want to show you that the sea breeze, the air over here tends to be cold. So we have this area of high pressure. And over here, the air over land tends to be warm, and that's lower pressure. And so what the air ends up doing is it travels this direction. But a sea breeze circulation is more than that. It's converging to the low pressure. The air goes up, it then travels this way, and then the air subsides. So this is really what a sea breeze circulation looks like in more like a cross-sectional view. So this isn't north and south, this is up and down. So whenever I draw a cross-section is going to be something like this, and I'm going to have these little lines like this. It's what we call hatch marks, H-A-T-C-H. And that always means the ground, and therefore this is always up. Okay? This is a cross-sectional view. I'm going to go over here and say cross-sectional view. So remember, if it's a map view, top down, north, south, west, and east, okay? Cross section, you see the line, you know that's up. So in a sea breeze, the air is traveling, ooh, I don't want that, I want this. The air is traveling this way, it goes up, it comes this way, and then it goes down. And then over here, if I didn't draw it this way, I'm gonna say, well, that's water, and then that's land. Okay? High pressure here, low pressure here. So that's how you do a drawing of this thing. And its differences in temperature are going to generate that. That's where we're going to. So we'll explain that later. Delete that. So they give you a little bit where they show you the video, and at night it switches into a land breeze. It's colder at land than over the water at night. That's important when we deal with fire weather. You're going to want to know these things. So, boom, there's the stuff that you need to go through, and I think that's a good place that we can take you at this point. Next time, I'm going to talk to you more about upper level winds, and then we're going to look at cross sections, and that's where it gets even more complex. The last thing we want to talk about is what are the forces that are acting on the winds? We know the pressure gradient force. That's what the air wants to do. We know the Coriolis force. Even though it's apparent, it still matters. The last force is friction. And I'm going to leave you with this thought right now. Friction wants to slow the winds down, but it will deflect the winds across the isobars toward low pressure. Write that down. Go back. Go stop me and go back a little bit. Okay, so when I go back here, you're going to see why this is what it is. I'm going to go back. Sorry. Okay. And over here, it's like, okay, see the air. So watch this. The air wants to go from high to low pressure. That's what it wants to do. But instead of going this way, it gets turned to the right, and now it's going to go parallel to the isobars. That's what it's going to want to do, or that's what it's going to do on the large scale, right? It's going parallel. But if this is near the ground where friction plays a role, the air is going to get slowed down, and it's going to deflect across the isobars toward lower pressure. So rather than being this big of an arrow going that way, it's going to be a little bit slower, and it's going to be like this. It crosses the isobars. Now it's about a 30-degree angle is good enough for this class. They're going to be a little bit slower, and they're coming across the isobars toward lower pressure. And so what that means is you get this flow, and again, I'm going to use my pen here, that the flow actually crosses the isobars and spirals in. Like that. Now, if I put a whiteboard on it, that's what you get. This spiraling in toward low pressure. So, mesoscale, air goes toward low pressure. The large scale, the Coriolis force goes, and now it goes parallel to the isobars. But those green lines are not parallel to the isobars. And the reason for that is friction is causing it to deflect across a little bit. So rather than just going straight in, which was the first diagram in red arrows there, or going parallel and just spinning in a circle, now the air actually spirals it, and it's got to go up because it's converging. You see that there's still convergence in the middle. High pressure, same thing, but opposite direction. It's going to diverge not parallel to the isobars. Oops, that's not what I wanted. Not parallel to the isobars, but deflects across the isobars toward low pressure, which is away from it. So over here, now you're starting to get flow that's going to be going like those black arrows, spiraling anticyclonically away from the center of the high. And that, mon frère, is what we needed to do with today's lecture. Now the next lecture is going to go into this in more detail, so this should be enough to get you started to finish the worksheet for this, this module. So go ahead and do that, and then you can start the next lecture. So I need to do this. I'm going to stop sharing. If you have any questions, please call me, and I will talk to you guys later. Have a good day.